Hello seniors, today we're going to see electronic assignment number 7, which is geometric series. We have seen already, if we remember the previous classes, we've seen arithmetic sequences and arithmetic series. Remember that arithmetic series is when we add all of the terms of an arithmetic sequence, right? So now we've also seen during the last class geometric sequences, okay? Remember that geometric sequences are terms which have a common ratio, in which the terms have a common ratio, right? A common division or multiplication between the terms, right? So today we're going to see geometric series, which is the same idea as an arithmetic series, is the addition of the terms of a geometric sequence. Okay, so we're going to see the formula for that, and then we're going to practice with some exercises. So the objectives for today's class. First one, use the formula of the sum of the first n terms of a geometric sequence and apply geometric sequences to solve problems. Okay. So, what is a geometric series? A geometric series, as I told you, is the sum of terms of a geometric sequence. Here's a quick demonstration of where the formula comes from. You don't need to know this demonstration, but I'm just going to show you for you to understand where the formula comes from. So it says, adding the terms of a geometric sequence gives the following equation. So this is the sum of n terms of a geometric sequence. U1 plus U2, remember that a geometric sequence, for the nth term of a geometric sequence is U1 times the common ratio to the power of n minus 1. That's how we calculate any term in a geometric sequence. So if you pay attention, this would be U2, the second term, this is U3, U4, and so on, right? So this would be U of n minus 1, and this would be Un, okay? So what we're doing in the first line is just adding all the terms of a geometric sequence. Then we will call this equation number 1, okay? Then what we're going to do is we will multiply equation number 1 times the common ratio r, okay? So r times s of n is, and then the first term multiplied by r, this u2 multiplied by r. So we're getting all of those terms, right? So it's the same thing, but with an r multiplied to it, okay? So we'll call this equation number 2. Then what we're going to do in the third line is we will subtract equation 2 minus equation 1. Okay, so r s of n minus s of n, and you'll see that all of the middle terms are eliminated. For example, this one gets eliminated with this one with this one, and so on. This one with this one. So we only this one also with this one. We're only left with the extreme terms, or the ones at the very end, which are this one and this one. And since we're subtracting, we're going to write minus u1 plus this term over here, which is u1 times r to the power of n, right? Which if we organize would be this, okay? u1 times r to the power of n minus u1. Okay. Then, if we organize the terms, you see that we can take a common factor of s of n, which is this, and inside the parenthesis we'll get r minus 1, and here we're going to get a common factor of u1, and in the parentheses we get r to the power of n minus 1. So finally, if we solve for s of n, which is the sum of n terms of a geometric sequence, we get the formula for the geometric series, the addition of terms of a geometric sequence, which is this: u1, the first term, times r, the common ratio to the power of n minus 1 divided by r minus 1. That's the formula, okay? So it says you can find the sum of the first n terms of a geometric series using this formula. This one, which if you see is the same as this formula. If we change the signs of the terms inside the parentheses, we would get positive 1 minus r to the power of 1. And in order to have the same equation, we should also change the signs of the terms we have down, right? So this would be 1 minus r. So you see that this formula, or this way of expressing the formula, is exactly the same as this one. Then why are we getting two ways of expressing the formula? Well, both formulas are the same thing, but in case you have, here it says, you may find it more convenient to use the first formula when the common ratio is a value greater than 1, as it avoids using a negative denominator, okay? So when r is greater than 1, we're going to use this formula, and when r is less than 1 and greater than 0, we're going to use this formula, okay? The absolute value of r, actually. So that's the rule. You can still use whichever you want, and you just need to pay attention with the negative sign that you're gonna be getting when you apply the formula. That's it. Okay. So this is this case, and this is this case. Okay. So let's see some examples to see how this applies. Calculate the sum of the first 12 terms of the series 1, 3, 9, and then we have the ellipsis until the 12th term, right? So pay attention that in this exercise, we're not being told what type of sequence is this, right? So first of all, we need to identify if it's an arithmetic or a geometric or neither. So what we're going to try to do first is try if it's an arithmetic sequence. So we're going to do second term minus first term. This gives us 2. Then 9 minus 3 gives us 6. So this is definitely not arithmetic, right? Now we're going to try if this is geometric. So we're going to divide the terms. 3 divided by 1 gives us 3. And 9 divided by 3 also gives us 3. So this is a geometric sequence with a common ratio of 3. Okay, so U1, the first term is 1, and the common ratio is 3. So if we want to calculate the sum of the first 12 terms, we're going to apply, in this case, we should apply this formula because the common ratio is greater than 1, right? So S of 12 equals U1, which is 1, times 3 to the power of 12 minus 1 over 3 minus 1. Okay, so S of 12 equals, can you use the calculator for this? This would be 3 to the power of 12 minus 1 divided by 2. This gives us 2, 6, 5, 7, 20, a very big number. You see that? Remember that geometric sequences behave like exponential functions. That's why we get very big numbers. If you want, you can try calculating the 12 terms individually and then see if the addition is actually that number. It should be, right? We could make a try here, although we're going to waste a little bit of time. You can fast forward this part. If we say that U1 is 1, U2 is 3, we're going to do this until U12. So U3 is 9. Then this would be, it's better if we use a menu table for this. This would be 3 to the power of x minus 1. So table set from 1 to 12, step 1. So these are the terms. This is 27, then we have 81, 243, 729, 2187. The ninth term is 96561. The 10th term is 19683. 11th term 59049. And the 12th term is 177147. So you see that we're getting very big numbers. And if you add all of this, you may try this on your own. If you add all of this, you should get this number over here. Okay, 265,720. Okay, so this is U12. So S of 12 equals that number over there. Okay, so that's it for the first example. Let's see now the second example. It says, find the number of terms in the series. Once again, we're not told what type of series is this, so we need to prove if it's arithmetic, geometric, or neither. So, first of all, we're gonna try if it's an arithmetic sequence. So, 6144 minus 8192. This gives us, let's see, 6144 minus 8192. Negative 2048. Then if we do 4608 minus 6144, this gives us, sorry, dyslexia over here. 4608, there you go. 4608 minus 6144, this gives us negative 1536. So this is definitely not arithmetic. Now we're gonna try if it's geometric. So we're gonna divide the term. 6144 divided by 8192. This gives us 6144 over 8192. This is 3/4, which is 0.75. And if we try with the next two terms, 4608 divided by 6144 is 608 divided by 6144. It's again 0.75. So once again, this is geometric with a common ratio of 0.75. Okay, so part A. Find the number of terms in the series. So we have U1, we already have the common ratio, and we have here the last term of the series. So this would be our UN, right? So remember the formula for the geometric sequence. UN equals U1 times R to the power of n minus 1. If you don't remember this, remember you can always go to the formula booklet, and here you have the formulas. This is the formula for the nth term of a geometric sequence, and the new formulas we're learning today are this. The sum of n terms of a geometric sequence, in which we have the first expression and the second expression, okay? You could choose either of those. Okay. So, we know that the last term, UN, is 1458. U1 is 8192. R, we know it's 0.75 to the power of n minus 1. Okay, so we need to solve this. There's a shortcut that you could use when applying the formula. Instead of trying to solve for n manually, you could just go to your GDC. So using GDC, I'm going to do it down here. Using the GDC, you could directly go to a menu, equation, and use solver. Okay, which is what Juani usually likes to use, menu solver. So if we plug in the equation into solver, we're going to directly get, I'm going to show you how to do this, but first of all I need to remember we go to menu equation, go to solver, then delete anything you have there and plug in the equation. 1458 equals 8192 times 0.75 to the power of x minus 1. Okay, so let me show you that using my calculator over here. So this is your calculator, right? So you go to menu, equation, which is the one we have down here, and you go to solver, which is F3, and then you plug in the equation, which is 1458 equals, to do the equal sign, remember it's shift and a dot, okay? Equals 8192 times r, which is, we're going to use parentheses here, 0.75, close parentheses, to the power of x. We're going to use x here because we don't use the n as a variable in the calculator, n minus 1, right? So you click on enter. Oops, syntax error. I don't know what happened here. Let's see. Suppose this is a dot, 0.75 to the power of, I'm going to use this x over here. So then, there you go. Okay, so you click on solve down here, which is, you can click execute, and then you get x equals 7. So this is the quick way of solving this type of equation. So if we go back, we know that n equals 7, okay? If you want to solve this manually, if you don't, for example, trust your calculator, remember how to do it. Let me see where I can solve this. Okay, so I'm gonna do it here. Solving manually. You can fast forward this part if you don't want to see this. So solving manually, what we're gonna do is, first of all, we can divide 1458 divided by 8192. This would be equal to 0.75 to the power of n minus 1. So we divide those terms, and this gives us 1458 divided by 8192. This is 729 divided by 4096, and this equals to 0.75 to the power of n minus 1. Then we need to apply logarithm, right? Because we want to solve for n, which is in the exponent. So logarithmic log in both sides, 496, and we would get n minus 1 times logarithm of 0.75. So then we take this dividing to the other side. So this would be logarithm of 729 over 4096 divided by logarithm of 0.75, and this equals n minus 1. If you solve that, this would be logarithm of that divided by logarithm of 0.75. I get 6. 6 equals n minus 1, so n equals 7. That's the long way to solve it, in case you don't trust your calculator. Okay, so that's it. N equals 7. Then part B. I'm gonna put a line over here to separate. So part B says calculate the sum of the terms. So we want to calculate the sum of the first 7 terms. S of 7 equals, according to our formula, if we go back to the formula, it's this one over here, right? So U1 is 8192 times r to the power of 7, so this is 0.75 to the power of 7 minus 1. This should be bracket maybe, divided by r minus 1, 0.75 minus 1. You see that in this case it could have been more convenient to apply the second form of the equation, because r is less than 0, greater than 0 but less than 1. But either way, I will get the same result, so it's the same thing, okay? So I solve this using the calculator, and we get S of 7, which should be, let's see, 8192 times 0.75 to the power of 7 minus 1 divided by 0.75 minus 1, and we get this number, 28394. which is the sum of the first 7 terms of this series. Okay, so that's it for this exercise. Now let's go on to this example. It says, for a geometric series, and we have first term, second term, pay attention at the terms, third term, fourth term, and so on. Determine the least value of n for which s of n is greater than 500. Okay, so once again, there are various ways of solving this. So, first of all, in this case, we're told that this is geometric, so we don't need to do a proof. So, u1 would be 3, and the common ratio would be 3 root 2 divided by the first term, 3. We can simplify this, and we get that the common ratio is root 2. Okay, so determine the least value of n for which s of n is 500. So I'm going to copy the formula here just for you to remember. The formula is s of n equals u1 times r to the power of n minus 1 over r minus 1. Okay, so one way to do this, I think it's the shortest way, is to just say that the sum, suppose it's 500, okay? Although it may not be exactly 500, equals u1, which is 3, times r. R is root 2 to the power of n, which we don't know, minus 1, divided by root 2 minus 1. And once again, you can use the same, you could do the same process using GDC, using solver, and you'll get a value of n by applying, by doing this, okay? So if you use solver, I'm going to show you once again, using our calculator. If we go back, we will change the equation, delete this one, yes. So it's 500 equals shift dot equals, and then we had a fraction, 3 parentheses root 2 to the power of x, right, minus 1 parentheses divided by root 2 minus 1. So then we solve, we click on solve, and we get that value of x, 12.26. So if we go back, we get that n equals 12.26. But remember that n can never be a decimal number. So we need to round this number where? To 12 or to 13? If we want the sum to be at least greater than 500, then we need to round up, okay? So n would actually be 13, okay? And this is the result. If you want, you may try doing this in a different way. You could either solve manually by doing this, or you can use menu table. If you remember from the exercise we did for arithmetic series, there was an exercise in which we plugged in this formula, and by observing the table, we identified the term which had a sum greater than 500, which would be term number 13. So then we would conclude that this is the least number of terms for which the sum of this series is greater than 500, okay? I'll let you try that by your own if you want. But I think that this is the easiest way to solve this using calculator. Okay, last exercise. It says a geometric progression has first term 0.4 and a common ratio 2. So this exercise gives us everything. U1 is 0.4 and the common ratio is 2. So find the value of n such that the sum is this number. Okay, so I think this exercise is pretty straightforward. We're going to apply the formula. 26214 equals u1, which is 0.4, times 2r to the power of n minus 1 divided by 2 minus 1. Okay, and once again, we need to solve for n, find the value of n. So we could just apply solver once again, right? So using GDC solver, we should get the result, which I'm gonna do it here quickly. This would give us solver 26214 equals u1, which is 0.4 times 2 to the power of x minus 1 over 2 minus 1. If you solve this, this gives us n equals 16. So that's it. You can try this by any other method. I strongly recommend using solver for this case. And that's it. So tomorrow we are going to be practicing with some exercises about this. Once again, if you have any questions, seniors, do not hesitate to ask this in the Google Classroom. I'll try to answer all of the questions as quickly as possible. Okay, so I hope you're doing fine and see you later.